This is lesson 5.9 on determinants. Now these past few sections we've been talking about matrices. When we're dealing with square matrices, so a square matrix is one whose height and width are the same. An important property, important thing that we can talk about these square matrices is the value of the determinant of that matrix. Now the general definition of a determinant is actually quite complicated. It's quite a bit beyond the scope of this class. So we're not going to worry about it. We're going to look at the specific examples of the determinant of a 2x2 matrix and a 3x3 matrix. You can find the determinant of a 4x4, 5x5, a million by a million. All these things still have determinants, but to calculate them, it's difficult. 2x2 and 3x3s, there are relatively simple algorithms that we can follow, and we'll discuss those. Now, the role of the determinant, when we see it, it's going to seem kind of a weird thing. We wouldn't think that it has much use at all. We're actually going to see one use of it in our next section, but this is not the only use of it. It actually pops up in a variety of places in mathematics. So the determinant is useful. Kind of a weird thing to calculate sometimes, but once again, we'll only deal with 2x2 and 3x3 matrices here. So we'll do a couple examples finding the determinant of a 2x2 matrix, and then for our application problem, we'll see how to do it for a 3x3 one. Alright, so here we've been tasked with finding the determinant of this 2x2 matrix. Another way that we will denote when we're talking about finding the determinant of the matrix is if we write the matrix and we use bars on the left and the right rather than brackets like we did before. To find the determinant of a 2x2 matrix, it's very quick, very easy. You're going to take the product of these two numbers and then subtract the product of these two numbers. So the determinant of this matrix is going to be 3 times 1 minus 4 times negative 2. So the product of these two numbers minus the product of these two numbers. So that's going to be 3 minus negative 8, so plus 8. So our determinant here is simply 11. These are very quick and easy. Finding the determinant of a 2x2 matrix takes 5 seconds max. Very quick, very simple. I would expect to see a couple of these on our drill portion. So be able to do these. We'll do one more quick example, and then we'll move on to see how we can do a similar thing when we're dealing with 3x3 matrices. Alright, one more real quick. So negative 5, 1, negative 3, negative 2. So the determinant is going to be negative 5 times negative 2, so positive 10, minus negative 3 times 1, so minus negative 3, so plus 3, 13. So once again, the determinant of a 2x2 matrix we can do very quickly, very easily. We're going to take a look now at how to find the determinant of a 3x3 matrix. It's still relatively easy to do by hand, but it's really the last one where it's simple to do so. 4x4 and higher gets pretty complicated. It is doable by hand, but pretty impractical. So 3x3 we'll see. We've got a nice algorithm for it. We'll see that in just a moment. Alright, so here we go. So find the determinant of this 3x3 matrix. So I'm going to go ahead and rewrite it over here. So we do have I'm still going to call it simple, but it's nowhere near as simple as the approach that we saw before. So here's how we find the determinant of a 3x3 matrix. So when we rewrite it like we've done for the previous problems, we're going to copy the first two columns again. So 2, negative 3, 1, negative 1, 0, negative 2. Okay, so we're going to do something similar to what we did last time, but again, kind of a little bit more complicated. So remember last time we took products at a diagonal and we added one and we subtracted the other. So here we've got multiple diagonals to deal with. So what we're going to do is we're going to take this diagonal right here and this diagonal right here, and this diagonal right here. So we're going to multiply each of these three numbers together and add them. So each of those are positive. Next, we're going to take this diagonal right here, this diagonal right here, and this one here. We're going to multiply those and subtract them. When we combine all those terms, positive, these are all positive, these are all negative, that will give us our determinant. So first up, we have our first blue line here, 2 times 0 times negative 1, that's just going to be 0. Negative 1 times 4 times 1, that's going to be negative 4, so we're adding negative 4. 1 times negative 3 times negative 2, so negative 3 times negative 2 will be positive 6, so we're adding 6. Okay, so we're done with all of our positive diagonals. Next we're going to do the negative diagonals. So first up, 1 times 0 times 1, so we're subtracting 0 from that. Negative 2 times 4, that's negative 8, times 2, that will be negative 16, so we are subtracting negative 16. And negative 1 times negative 3 times negative 1, so negative 1 times negative 3 is positive 3, times negative 1 is negative again, so we're subtracting negative 3. So once again, this diagonal gave us plus 0, this diagonal gave us plus negative 4, this diagonal gave us plus 6. This diagonal gave us minus 0, this diagonal gave us minus negative 16, and this diagonal gave us minus negative 3. So putting everything together, we've got negative 4 plus 6, that's going to be 2. Minus negative 16, that's going to be just plus 16. Minus negative 3 will be plus 3. So 2 plus 16, that's 18, plus 3, 21. So a 3 by 3 determinant isn't terrible, but clearly more complicated than just a 2 by 2 one. We will always use this technique though. We'll take the down right diagonals, and those will be positive. Multiply these three numbers together, add them up. So 1, 2, 3 corresponds to 1, 2, 3. And then for our negative ones, 1, 2, 3 corresponds to 1, 2, 3. So we're always taking three diagonals. 3 positive diagonals, 3 negative diagonals. So if you remember this, this shouldn't be a terribly difficult or time-consuming problem if we run into this on the application portion. So I hope that we're able to get this. This is meant to be honestly one of the easier application problems that we might run into.